All right, guys. So we're on our third project now, and we're doing the 2D wind tunnel simulation. And we're given our constraints, and we're given our velocity constraint for the test section, and then we're going to be testing it at different motor frequencies in the wind tunnel. So of course we're going to be using ACES, and as always, we use Fluent. Drag it over here, and then geometry. We're going to do design modeler. So I'm going to show you guys how to design everything in here. But I know you guys can design stuff in like SolidWorks or any other sort of CAD software and import it in here. We're just gonna do everything on ACES today. So we're gonna go normal to XY, and then we're gonna go into our sketching. We're gonna use a line. Now I'm gonna start this line below the axis and come up. And I'm gonna show you guys why in a sec. You'll understand why I did it like that. Just wanna make sure the line was there. And then let me redo that line actually. That's showing me weird. Yeah, so just gonna do a line below the origin. And then we're gonna come here to constraints, and then we're going to do a midpoint. So we're going to select the line, and you're going to select the origin, and you'll see why that becomes very useful in the end. And then we're going to dimension this line. I'm going to general. I'm just going to come out here, and we'll change the units to inches. And we're going to do 22 for the inlet was our constraint. And we're going to zoom in a bit. It's way too much. Move over a little bit too. All right. So now we're back. We're gonna draw. We're gonna do another line. We're gonna come here, and then we're just gonna draw the rest of how it kind of looks. We're gonna come here. And the only reason why I'm not doing them crazy is because I'm gonna dimension them in a second. So for the dimensions, this one is gonna be 15 inches. This one here is going to be 24 inches. This one here is going to be 12. And this one here is going to be 42. And then we have an angle here of 3. So A6 is going to be 177, because that's 180 minus 3. Where I'm getting that from is where you see that half diffuser angle. And then also too, for the test section, we know the height is 6. So for the bottom part to the midpoint, it would be 3. We don't have the top half built yet. I'll show you. We're gonna get there, but for now, I'm just gonna put a vertical dimension from here to the midline, and I'm gonna have this as 3 inches. All right. So what I'm gonna do is I'm going to use a tool to duplicate everything or mirror it. So I'm gonna grab all of my lines that are here first, and then I'm gonna grab this replicate tool, and then we're gonna change this to 180 degrees because that's where we're going. And then it says indicate handle. We're gonna use this as our handle. Sorry about that, y'all. Just gonna right click here. So we're gonna do that again. We're gonna just escape. We're gonna hit control. We're gonna grab all these lines. And then we're gonna go to replicate. And then the handle is gonna be the top of our line. And then we're gonna right click to do flip vertically. And then we should be able to just place it. It should kind of like stick onto it, and it'll let you place it. But yeah. So we have everything here. Now we're gonna do the same thing. We're gonna dimension it all in the same. What I'm gonna do first is I'm gonna add a line at the end. That's the outlet. And I'm going to dimension everything else. So we're gonna just make sure everything is the same. So general, this is gonna be 15. Usually it is all the same, but you just want to always make sure. Because where did this go? That's 10, that's 12. I'm just reading them off here. I'm seeing how they're added and everything is looking the same. 42. And then we're going to do a vertical. Whereas this is going to be 12. It's going to be 6 inches. And then I have to do an angle from here to here. A13 should be 177. Now, if we do the angle from this line to this line, it should say 183. I'm going to undo that angle just so you can see what I'm talking about. So if you end up doing it from here to here, it should say 183. And it would be the same because it's flips the opposite. So it should be 183. So it's all the same, plus 3, minus 3. And that's that 3% angle. So what we're going to do now is we're going to go over to our model. We're going to do concept, surface from sketches, sketch 1, apply, generate. And then we have our surface. So this is pretty much just how the wind tunnel is, and you're going to see why I went below the origin so that this is our midpoint. And then now we're just going to open up our mesh. I'm going to just update this real quick just to make sure that it's all good. And we're going to go into mesh. We're going to mesh everything up. But how we're going to divide the shape is going to be a little bit different than what we've done before. We're going to use triangles. So you'll see. It's going to be really easy too. So mesh. I'm going to insert a method. Sorry. Select this. I'm going to do apply. And we're going to change the method to be triangles. And we are going to generate it. So I'm going to go back to mesh. You can see it here. And we're going to change our element sizing to 0.01. And then go back in mesh, generate it. Sorry. Back in mesh. You can see everything is divided up pretty small. All right, so then now we're just going to do the edge. We're going to name everything. So we're going to grab our edge. We're going to do 1, 2, 3, 4. This is going to be walls. Okay. Inlet. Outlet. And then we have everything here. Just wanted to make sure everything was on there. Sometimes it doesn't grab everything. I can see that everything was grabbed. It's a part of tunnels. All right. So we have all of our surfaces. And then now we're going to update the mesh. And then go into the actual simulator. So we're going to do 4 solver processes. Start. So obviously if your CPU is powerful enough, multiple cores. Same deal as always, yeah. I was gonna wait for this to load. And the simulation itself isn't gonna be too crazy. All right, just waiting for this. Damn, this is really loading. But yeah, once this loads up, I'm gonna do everything. All right. So first thing first, we're just gonna jump in and kind of get this rolling. We're gonna go to energy. We're gonna put the energy equation on, and then we're gonna go to viscous. Gonna edit this. We're gonna use K epsilon standard, and we're gonna do um, enhanced wall treatment, and then we're gonna do pressure and gradient and thermal effects, and everything else. Just gonna cross reference it. Everything else should be okay. We're gonna go into just checking on everything. Boundary conditions. We're gonna go to our inlet. Actually, let me double click on boundary conditions and then you can see everything. We'll do it from here. So inlet should be on velocity inlet. And I'll edit this. So for our velocity magnitude, what comes in handy is understanding that this is all continuity and this is conservation of mass. Sorry, yeah. So yeah, what I was trying to show you guys was so we're trying to find our inlet velocity here for the settling chamber. So what we're doing is um for the settling chamber, how we're gonna go about doing that is, doing continuity, so conservation of mass. And as you can tell here, we have the fan is actually at the end of the diffuser at the outlet. So that's what the motor is running at these different frequencies, and that's what we're testing it. So the two areas that we're concentrating on is the settling chamber and the test section. So if you do conservation of mass and you have A1 V1 is equal to A2 V2, we know that the areas that we're looking at are the two heights of these sections. So the test section area, um, the test section height, sorry, is 6, and then the settling chamber height is 22 inches. And then we know the outlet velocity or the test section velocity is held by this constraint, and we're using the motor frequencies. So for example, at 20 hertz, you would plug in 20 for F, and then you would get the velocity of the test section. So when you do that, you'd use your calculator. I have my TI here. You would get that the test section velocity at 20 hertz is actually 4.6062 meters per second. And then you would then plug, and then now, since you have a A1 V1 is equal to A2 V2, that settling chamber, which is our inlet, that velocity is going to be A2 over A1 times the test section velocity, sorry. So then at that point, you would do 6 inches divided by 22 times that 4.6 value here, and then you would get 1.25 and then like some other remaining numbers. So we're gonna actually plug in that number because we're testing it at 20 hertz first. So we're gonna get 1.25611.074. I'm just reading it off my calculator. So I'm looking at my notes too because I had everything written down for like how I had to solve that kind of notes. It's a little confusing to figure it out. But basically you're just doing conservation of mass, but you're looking at the settling chamber and the test section. And the settling chamber is the inlet. So that's gonna be your A1 V1. And then the test section is your outlet. So that's gonna be your A2 V2. And you're just gonna manipulate the equation to then get that inlet velocity. And you're gonna do that at every frequency. So you'll continuously go back, plug the value in for 40 hertz, 60 hertz, and then do the exact same equation again to then get the inlet velocity at that frequency. But once we set that up, we're going to just go into our reference values briefly and then just check for the inlet what the velocity is reading at, and then boom. So I change it to the inlet, and then now we're going to go to initialization. And then we're going to initialize, and don't worry about the tolerance. And then we're going to do run calculation, and we're only going to do 100 iterations just to kind of keep it smooth, kind of get everything rolling, and we're going to calculate it. We'll get these residuals going, and then you'll see the residuals for the most part should be pretty smooth. But then yeah, so we have our residuals. And then now the next thing that we're going to be looking at is the contours. So we need our contours for every sort of our velocity, static pressure, dynamic, total pressure, and then we're going to do the plot. So for that, we're going to go back in Fluent, and then for contours, we just jump into our graphs, and then we're going to do contours. We're going to do new, but then this one is going to be our velocity contour. Can't spell. is going to be our velocity contour. So we're going to do velocity, we're going to do velocity magnitude, and we're going to select all the surfaces. All right, and we're going to do save and display and then close. So then you would snap a picture of this using the Windows snipe tool or snip tool, and then you would just boom. But yeah, this is our velocity contour at 20 hertz. And then you would, then, you know, you can do another contour, and then this is going to be our static pressure contour. Then you can do pressure, static pressure, and you would select all the surfaces as well. Then you do save and display, same thing. And then we're gonna do dynamic pressure. I'll select all the surfaces, change this to dynamic pressure. And we have it here. This is all at 20 hertz, by the way. Then you do new. Then we're gonna do total pressure contour. Then we're gonna do total pressure. And then boom. So yeah, those are all the contours. And then for the plot or for the graphs of everything, and then you can see actually that you have all the contours. I like to create new, so you have all of them. You can go back between them, but then you can go to plot and you'll do XY plot. You'll do new, and then here's where we're gonna do we'll do the velocity first. The velocity graph, and then here we'll change this to velocity, and then we'll change that to direction vector. But we're gonna create a new surface because we're actually gonna look at it from the center line, which is why we did everything and have the origin as our center line. So our x 0 would be 0 because we're starting at the inlet, and then we're trying to find how long our chamber is, our entire chamber is, and then obviously height wise we're at the origin. So to figure out how far out we're going, we're going to open up the design model, and then we're going to do tools, and we're going to use distance finder. So here you're just going to select. All right, we're good. Sorry, my OBS had crashed. So yeah, we went back into the design model because again, we're here, we're trying to figure out our X1. So we're gonna go in here, we're gonna go to units, and we're gonna use meters. I changed it to meters. Because remember we had it on inches, so we're gonna change it to meters because we're gonna find that distance. Then we're gonna open up tools, and then we're gonna go to analysis tools, distance tool, and then I'm gonna use the edge selector tool, and I'm going to select this edge here, and I'm going to apply it. And then this one is going to be there, and I'm going to apply it, and it's gonna give you that distance in meters for how far apart that is. So you're gonna plug in 2.3259. So you have, where are we at? 2.3259. Let me just verify that that was correct. 2.3259. Yeah. So then that'll be your X1, and then you'll create it. And then actually, what we're gonna do is we're gonna name it center line. I don't know why I didn't do that. And create it. Close. So we'll actually. I don't know if it would let me delete that, but I mean, it's the same thing, but we're going to use center line. I created two by accident, but we're going to use a center line. And yeah, so you would have that there. Your center line is there. Then you do save and plot. And then this is your velocity. And you could do the same thing. You do another XY plot. And then you're going to do static pressure graph. And then you do center line. And then you do pressure. Static pressure is already there. Directional vector. You save and plot. Then boom, that's your static pressure. And then you're going to do dynamic pressure graph. And then you're going to do dynamic pressure, dynamic pressure from the center line, save and plot. And then you're going to do total pressure. And this is going to be total center line, directional vector, save and plot, and then boom. And then this is gonna be your test case for 20 hertz. So again, like I was saying before, you have to test at each frequency for the motor. Um, so now you would do 40 hertz. So then you would plug 40 into this equation, and then you would then do the same thing, like I said before, doing conservation of mass. So if you do that successfully, your V1 now, which is the inlet, should now jump up to what is it, 2.61 just about. So we'll go back and fluent. Now all we're gonna do is we're gonna go to our boundary conditions. We're gonna go to the inlet and we're gonna edit the inlet velocity. And we're gonna change this. Actually, further down, I'm gonna close the total pressure graph because it's gonna kind of glitch out once you change everything. And I'm gonna go to here. Sorry, I'm already here. Edit, and we're gonna change it. And you don't have to put all of the values or all of the decimals, that decimal places, but I'm putting it just to be as like spot on. And then I always go back into the reference values just to make sure that it updates to the new velocity, which it did. So it's 2.61. And then, um, did it take everything? I know for the boundary, I put all the values in. It didn't take the whole number. That's fine. And then you're gonna just go to your contours and then your plot and then just view the same thing. So you'll go to graphs, you'll go to contours, or actually no, you'll go to initialization. Sorry, you have to run everything again. So you'll initialize it one more time. You hit OK because it's gonna erase the data from the last one. Run calculation, keep it at 100 iterations, and you'll calculate it. And then you'll go to the graphs. After it calculates, you'll go to contours. So then yeah, that's all the old stuff. And then you'll go to your velocity contour, for example. You'll do edit, you'll do save and display, and then you'll see the values are different. And then you'll do the same thing. You'll like basically take pictures of all that. The same thing for static. You'll do the same thing for dynamic. Same thing for total. And then for your XY plot, you'll do the same thing. So you go to edit, you'll do save and display. Then you'll see that your values should be different. And you're just editing it, save and plot, total pressure graph, save and plot, close. And then of course, you know how to get everything in Excel. You do write to file, you'll write it, but you're just doing save and plot and closing it. And that's how you'll get all the values. And then you'll do the same thing once more for your 60 hertz. So when you do for 60 hertz, you know your velocity, have it on my calculator, it would jump up to 3.97194. Then you can do apply, you apply it again, close, reference values. I just like to make sure so it changed. You know, it doesn't like to take everything. But you'll go right back into initialize. I just initialize it and calculate everything over again. Pretty sure you could just jump right in with the new values, but you definitely want to run the calculation again. I should have closed it, the total pressure graph, but it's okay. So our residuals are here. And those residuals are definitely different, so you can see how steep the data starts to get. I just closed that by accident, but essentially now that I'm in there, or did it just crash or did I close it? Either way, it would be in Fluent with the 60 hertz calculation. And then now you're gonna just do everything that you did before, and it should load everything back up um, as the same. But if in case it doesn't, we can just redo it. Should be fine. Dang, it's just loading forever. All right, so gas, contours. All right, everything is still here. So we're chilling. All right. So we're gonna go to boundary conditions, and then we're gonna go back to the inlet. We're gonna just make sure that it's at 60 hertz, which should be at our 3 point. Yeah, yeah, yeah. So it's good. I'm just gonna just double check everything real quick. But y'all get the idea of how to do this. I don't even have to pretty much watch this whole thing. I'm just gonna do everything again though. I'm gonna initialize it. I'm gonna run the calculation again. 100 conservative. Just doing it just in case if it didn't actually capture anything. Yeah, it's gonna run through all that. It's gonna show it. And then yeah. So you just do the same thing. You'll go to velocity contour. Um don't add this line 4 here. That's you'll just leave everything as is. Don't add the line 4. You'll just do save and display, then close, and then static. Same thing, save and display, close. This is at 60 hertz. This is dynamic, save and display. This is total pressure, save and display, close. And then XY plot, do velocity graph. This is at the center line. Save and display, close, static pressure, save and display, dynamic pressure. And yeah. So yeah, you'll have all of that. You could write the data, port it into Excel, and you pretty much just have everything there. And then you would definitely have satisfied everything. You tested it at the different motor frequencies. You use the constraint for the test section, and you use that to then calculate the velocity at the settling chamber, which is the inlet. And yeah, you would just tabulate some of that data, take photos of everything, and you would be good. All right, yeah, this is project number 3, 2D wind tunnel simulation at different motor frequencies. And I'm gonna see y'all next time.